Okay, we're going to continue looking at improper integrals, ones involving infinite limits of integration. So here we see in this one going from 2 to infinity, so we have an infinite limit of integration. But before I transform it and write it in the limit form, I'm going to note that to make things a little bit easier, I'm going to do a little substitution here. And that is I'm going to let u be x plus 7 so that du is dx. Now you don't have to do a substitution here. It's not too bad, but I'm going to do it this way to make sure everything's clear. Now we do have a little adjustment though. When we change variables, we also have to change the limits. And I just want you to note with the limits, the bottom limit x equal 2, what does it become in terms of u? It's x plus 7, 2 plus 7, so it's 9. What about the bottom limit now, or top limit rather? I mean, x can't be equal to infinity, but it's approaching infinity. Well, what happens is x goes to infinity for u. U is x plus 7. If x is going to infinity, then x plus 7 is also going to infinity. And so, that doesn't change. The upper limit is still going to be infinite. So when I make the change to the u world, what do I have? This 5 is a constant multiple. Let me just pull that 5 out. And my new limits are what? From 9 instead of 2, still to infinity. And I've got the dx is just the du, and this is u to the 3/2, right? And so, we'll write it this way. Okay, so there it is now in terms of u. So that just cleans it up a little bit. Now I'll do the limit notation. So this is the limit as t goes to infinity of 5 times the integral from 9 to t. And now I'll rewrite this as what? U to the negative 3/2, so I can use the power rule. Okay. So what's the antiderivative of u to the negative 3/2? Power rule. Add 1 to the power. I get u to the negative 1/2 divided by negative 1/2. It's the same as multiplying by what? Negative 2. And we're evaluating this at the upper limit of t and lower limit of 9. Now this, obviously, I can rewrite, well, 5 times negative 2 is negative 10. And u to the negative 1/2 is what? 1 over the square root of u. 1 divided by u to the positive 1/2. And so if I factor out that negative 10, then what do I have? I have 1 over u is t minus 1 over 9, square root of 9. U is 9. Notice I don't go back to the x's, right? Don't go back to the x's. I stay here. These are u limits, right? So I don't ever go back to the x world. I did forget something. I apologize. I would get on to you guys for this. So let me plug in my limit as t goes to infinity, because I haven't taken my limit yet. Okay, but I'm about to, because what happens as t goes to infinity? Well, this doesn't change, this doesn't change, but what about this? As t goes to infinity, what happens to this? This is clearly going to go to 0, right? Square root of t is going to infinity, so 1 over square root of t is going to 0. And so this becomes negative 10 times a negative, well, of course, what is square root of 9? That's going to be just 3, right? So this is negative 10 times 0 minus 1/3, negative 1/3. I get positive 10/3. Okay? And so the integral converges. And its value, this is the value of the integral. Notice we knew it was convergent at this point. Essentially, we have it in the form, so it's basically a p integral at this point, right? You have, here instead of x, I've got u, but u to the 3/2 power. And so the value of p was 3/2, which is greater than 1. So we looked at that in the last video. So this is essentially, it's kind of, because it's just not x, you've got to do this little substitution to get it. This is essentially a p integral, like we looked at. This next one is also essentially a p integral, but it's got to do some work to it as well with another substitution. So notice this one goes from negative infinity to 0, so we're going to see how one of these work. Let me first change the variables. What would I let u be if I'm doing a substitution? What would I let u be in this case? I hope you're saying x squared plus 9. So my du is 2x dx. I notice I have a 4x dx, so I'll just cover that by multiplying both sides by 2. 2 du equals 2 times 2, 4x dx. Don't forget my limits, right? Now the lower limit, and this is going to be interesting, x is going in the lower limit to negative infinity. Okay. Well, what happens to u as x goes to negative infinity? Well, if x is going to negative infinity, notice when I square a negative number, what happens? It's positive. So if x is going to negative infinity, x squared is going to positive infinity. So u, right, is going to positive infinity. So that's a little different thing there you have to realize. You have to think about what's happening. The upper limit, x is 0. That's easy. U is what? 0 squared plus 9 is just 9. And so what does our integral become? It becomes the integral from positive infinity to 0. 4x dx is the 2 du up top, all over what? The square root of u, or u to the 1/2 power. Now, it's kind of weird seeing the infinity down here from what we've seen, and so what I'm going to do is I'm going to swap the limits of integration. In order to swap the limit of integrations, what happens? What do I have to do? Do you remember? Put a little negative sign out here. Let me pull this 2 out, negative 2. Now I can swap the limits of integration, and du over u to the 1/2 is u to the negative 1/2 du. Alright, so all that, now I can write it in the limit form. It's the limit as t goes to infinity, negative 2, 0 to t. Now I can take the antiderivative. It's the antiderivative of u to the negative 1/2. If I add 1 to negative 1/2, I get positive 1/2. So u to the positive 1/2 divided by 1/2 is 2 times u to the 1/2. Negative 2 times 2 is negative 4. So I get negative 4, and u to the 1/2 evaluated at t is t to the 1/2, or square root of t, minus 0 to the 1/2, which is just 0. And now we have this, basically we're taking the limit as t goes to infinity of negative 4 times the square root of t. And as t goes to infinity, square root of t is going to infinity, but notice this is negative 4, so this whole thing is going to negative infinity. The output is getting more and more unbounded, but it's always negative. Okay, so what's this mean then? The integral diverges, since the limit is not a finite value. Okay. Again, at this stage, we can actually look at this as being a p integral in a sense. Instead of x to the p, I've got u to the p down here, where p is a half. And if you remember, if p is less than or equal to 1, then the integral p integral diverges. But again, you don't have to memorize, that to do these. You can still work them out just like I've done these. Okay, the next two are not going to be p integrals that we're going to do. So let's take a look at 2 more examples. So here we have the integral from 0 to infinity of x times e to the negative x. Okay, so let's write this out. This is the limit as t goes to infinity, integral from 0 to t, x e to the negative x dx. Now, how am I going to do this thing? How am I going to find the antiderivative of x e to the negative x? I'm going to look at this just by itself because we've got a little bit of work to do, don't we? What's the antiderivative of x e to the negative x? How am I going to do that? What process am I going to use? Do you remember these letters? What do they stand for? Integration by parts. Integration by parts, right? I'm going to let u be what? X or e to the negative x. Remember liate, log, inverse trig, algebraic. Algebraic is x. And therefore my dv is e to the negative x dx. du is dx. And what do I do here? I integrate, right, both sides, and I get v. What's the antiderivative of e to the negative x? It's negative e to the negative x. There's a little substitution we do in there. Okay. So hopefully you remember the integration by parts. Just remind you the integral of u dv is uv minus integral v du. So this will be uv, which is negative x e to the negative x, minus v du. But minus v, that's going to be plus, right? Minus a negative is plus. V is negative e to the negative x, but minus becomes plus e to the negative x. And du is just dx. But what's the antiderivative of that? We just talked about that. That's negative e to the negative x with a simple substitution. Okay. So this is just a little aside to realize sometimes when you find the antiderivative, you've got to use some of these other techniques that we've been working with. So this becomes the limit as t goes to infinity. The antiderivative of x e to the negative x is negative x e to the negative x plus a negative or minus e to the negative x. Okay. And so what do we get here? We get the limit as t goes to infinity. If I plug in t here, I get negative t, and let me write this as negative t over e to the t, right? E to the negative t is 1 over e to the t. And minus what? 1 over e to the t. So that's what I get when I plug in t. What happens when I plug in 0? Of course, this is 0, so this whole thing is 0. Minus what? E to the 0. What's e to the 0? That's 1. 0 minus 1, that's a negative 1. Of course, we're going to get minus a negative 1. We're going to get positive 1 there. All right, well, let's take a look at this then. Let's clean this up a little bit. Got minus t over e to the t, minus 1 over e to the t, plus 1, as we say. Well, certainly, as t goes to infinity, now we'll evaluate the limit. This 1 isn't changing. We know what's happening here, right? E to the t is going to infinity, so 1 over e to the t, that's clearly going to 0. But look at this. As t goes to infinity, t is going to infinity, and e to the t is going to infinity. So what do we have here? Let's look at a little side here. What's the limit as t goes to infinity of let's just do it as positive t over e to the t, and then we'll multiply the result by negative 1. But this form is what? Is infinity over infinity. How do we find limits of that form, or how can we find limits of that form? You remember? When I invoke this property, I usually do this. What does this stand for? Does anyone have an idea what that big L stands for? What in the world am I talking about? This is L'Hopital's rule. And I mentioned that in the previous video, that comes into play. You remember L'Hopital's rule? The limit of a ratio of two functions, if it's of the form infinity over infinity or 0 over 0, is equal to the limit of what? The derivatives of the top and the bottom, the ratio of the derivatives. So what's the derivative of t? That's 1. What's the derivative of e to the t? That's e to the t. Well, now I can take the limit of this thing as t goes to infinity, right? This is going to 0. And so I can also say that this thing here is going to 0. And therefore the limit is equal to 1. And the integral converges. So I would encourage you to review L'Hopital's rule that we learned in Calculus 1. It's a pretty simple one, actually. But it is helpful when we have limits of this form. Okay, we're going to do one more and then take a break. Look at, in the next video, some other types of improper integrals. This one here, notice, has infinite limits of integration for the upper and lower limit. Okay, so how in the world am I going to accomplish this task? Well, what we do is we split this up into two integrals, and its domain is all real numbers. Notice, the denominator is always 1 or more. So, in fact, here's the graph. This is something you might recognize as a bell curve. Looks like it's similar to a bell curve, and so there's many distributions that are like this. The Gaussian distribution that are used in normal distributions, and lots of probability calculations involve functions that look like this over infinite intervals. But I'm going to pick 0 in this case. In other words, I'm going to look at the integral from negative infinity to 0 of dx over 1 plus x squared, and add to it the integral from 0 to infinity. So I'm splitting it up basically in two parts, right here at 0. I'm going to look at this section and this section. Now by symmetry, it's going to turn out if this section is finite over here for values less than 0, then this area greater than 0 under the curve will be the same. We're actually going to see both of these integrals converge, and the values of each of them are the same. But we'll do each one separately and show that. And that's the only way this integral will converge. If both of these integrals converge, then this integral converges. If either one of these integrals were to diverge, either one or both, then this integral diverges. Okay, so let's take a look at it. This is the limit now as t goes to what? Minus infinity. Right? Because our lower limit is going to negative infinity, so I let t be down here and go to minus infinity. And then over here I have the limit as t goes to positive infinity. Alright, now comes the test. Who recognizes the antiderivative of 1 divided by 1 plus x squared? If you've been doing your partial fraction decomposition homework, you've probably run into it a few times. What's the antiderivative of 1 over 1 plus x squared? It's the inverse tangent or arctangent function, which we talked about in the last video, if you remember. Same thing here. Okay. And so I have the limit as t goes to minus infinity. And I've got tangent inverse of 0 minus tangent inverse of t. And here I have tangent inverse of the upper limit t minus tangent inverse of 0. Now, tangent inverse of 0, what is that? Well, that is 0. Tangent inverse of 0 is 0 because tangent of 0 is 0. You can go back and look at the graph that we gave in the last video to remind yourself of that. So what do we have then? What's the limit as tangent inverse, as t goes to minus infinity of tangent inverse of t. What's the limit as t goes to minus infinity of tangent inverse of t? Well, I'll just pull out this sheet from our last video, and I'll remind you, as x goes to infinity, the tangent inverse function is going to pi halves. As x goes to minus infinity, the tangent inverse function is going to negative pi halves. Right, here's the graph. Pi halves this way, negative pi halves this way. And so as t goes to negative infinity, then we have this thing here going to negative pi over 2. And as t goes to infinity, this thing here is going to pi over 2. So what's my limit here? 0 minus a negative pi over 2? That's pi over 2. That's what this whole thing here comes out to be. Plus, what's this whole thing come out to be? Pi halves minus 0? Huh. Pi halves. Notice, as we said, both of these integrals are convergent. Both of these two integrals are convergent, and their values are the same. In fact, the pi over 2 is the area under the curve from 0 to infinity. So the area under the curve for values less than 0 all the way to minus infinity because of symmetry. Of course, pi over 2 plus pi over 2 is just pi. And then so the original integral converges. Now I did this one choosing 0 as my sort of intermediary point here, but you could choose any other number. I could choose 1. I can go from minus infinity to 1, split it there, and then from 1 to infinity. The only problem is it gets a little messy when you're taking the tangent inverse of 1. So if I have a choice of 0, that's a pretty good number to use in a problem. I would typically use 0. But any number could be used to split this improper integral into two different improper integrals to evaluate. Okay, so that ends improper integrals that have infinite limits of integration. In the next video, we're going to look at improper integrals that have a vertical asymptote.